Yes, question number 15 deals with what? Factors on which nuclear stability. You have already dealt with the stability of an electron in an atom or stable atoms. Here it is nuclear stability. Point number 1. Yes. Binding energy per nucleon. What was the graph? Yes. Covered a number of times. This is binding energy per nucleon graph. This is number of nucleons. Higher is the binding energy per nucleon, higher is the stability. High binding energy per nucleon means more stability. That is 1. 2. If you plot number of protons and number of neutrons, N represents number of neutrons, Z or P, it's written P or Z here, so that we are in resonance with the notes. N is what? Neutrons. Z is what? Protons. If I mark a dotted line making an angle 45 degree, any point on this, X is 1, Z is 1, N is 1, Z is 2, N is 2, Z is 4, Z is also 4. This line is N is equal to Z line. Number of neutrons is equal to number of protons. When you plot this graph violates this line. Example is sodium. How many protons are there? 11. So you mark 11 here. Protons are 11. For sodium, 11 protons. That means Z is how much? Yes, Z is 11. Z is 11. Number of neutrons, 12. So it is 11. This point is not here. It is somewhere at this point. Number of neutrons are more, 12. Uranium, yes, 92 and 235. Total number nucleons is 235. Number of neutrons is very large. That means what? As the size increases, the graph deviates from this line. Why this gap increases? That is what the question is. Why number of neutrons are more in comparison to number of protons in heavy nuclei? Anyone with the answer, please? Small size nuclei. Suppose you have two protons. They have repulsion, electric repulsion, positive repel. And at the same time they have attraction also, nuclear force. Nuclear force is more than electric force for small nuclei. As the size of the nucleus increases, you have two protons at certain distance. Electric force will also decrease, nuclear force will also decrease. Decrease in nuclear force is much more in comparison to decrease in electric force. Why? Nuclear force is, yes, short range force of the order of 10 power minus 14, 10 power minus 15 of this order. That is why you need certain material, some element, those are, yes, having nuclear force but no electric force of repulsion. What is that element? Neutrons. That is why you need, as size increases, number of neutrons to number of proton value becomes more than 1, and this ratio keeps on. Here it is 1. Helium, 2 protons, 2 neutrons, 1 is to 1. sodium 12 by 11. Then as this number increases, this value keeps on increasing, say 1, 1.1, 1.2, 1.3, 1.4 of this order. Point number 3. Sum of the combination, periodic table, end of periodic table, gases, yes, helium, neon, argon, krypton, these are more stable because they have filled orbits. Agreed? Complete. Similarly, in nucleus also, certain combinations are more stable. Certain combinations of neutron proton are more stable, and it is the observation from the full table, all elements in the periodic table, nuclei. Yes, which one is most stable? Even means what? Number of protons and number of neutrons are even. 2, 2, 4, 4, 6, 6. They are more stable than even odd combination, and this combination is more stable than odd. So this stands for even combination. This stands for even odd combination, and this stands for odd combination. So 3 parameters. Number 1 is, yes, binding energy per nucleon. High value of binding energy per nucleon means more stability. Number 2 is, as size increases, why you need more neutrons? Answer is, for small nuclei, proton repulsion is electric, attraction is nuclear, small distance nuclear force is very strong. As the size increases, both electric force and nuclear force decrease, but decrease in nuclear force is much more in comparison to electric force. So you need some material, some basic particle which will have nuclear attraction but no repulsion. That means neutral particle. What is that? Neutron. So we need more neutrons for stability. As the size of the nuclei increases, this ratio also increases. That is why this graph deviates from which line? NZ line. This line is termed as NZ line. Helium lies on this. Helium, yes. How many protons? 2. How many neutrons? 2. So helium lies on this line. Time with you is 3 minutes to write. Refer to numerical number 28. Numerical is an isotope of uranium-238 decays successively to form thorium-234, barium-234, uranium-234, thorium-230, radium 226. What are the radiations emitted in these 5 steps? So what is given? Uranium 238 changes to thorium 234, 90 plus something, we don't know what it is. Then thorium 234, 90 changes to Palladium plus something, we don't know what it is. Then Palladium changes to, this is Palladium 91, 234 changes to Uranium 92, 234 plus something. And Uranium 234 92 changes to Thorium 230 90 plus something, and this thorium changes to radium 88 226. Completed. 1 minute. Yes, first step I will help. This is 92, this is 90. What you get is 2. This is 238, this is 234. What you get is 4. Yes, helium nucleus. So first is what? Alpha particle. Try the next one. Complete all equations. Next one. Yes, it is 90. On left side it is 90, right side it is 91. What you need to have is minus 1. This is 234, this is 234, this is 0. 234 plus 0 on right side is 234. 91 minus 1 is 90. This, yes, beta particle. So decay is beta. We refer to this then. Yes, 234, number of nucleons same. This is 91, this is 92. What should we have here? Minus 1. 92 minus 1 is 91. Here it is 234, this is 230. Yes, 4. It is 92, it is 90. 92 minus 90 is 2. It is helium alpha particle. This is 90, this is 88. Yes, 2. This is 230, this is 226. 230 minus 226 is 4. So, alpha, beta, again alpha and alpha.